Hi everyone, thank you for the introduction. I'm excited to present our recent work in the field of digital pathology. And to give you some motivation to listen, this work was recently published in JAMA Journal, and as well as a few newspapers. And I have a really nice photo of me there. So my talk is going to include 3 parts. Let's start with a short introduction. So when we have a suspected tumor in our body, the first thing that we do is to take a biopsy sample out of it. So we take a needle and we sample a small part of the tissue, and we give this sample to a pathologist in order to examine it under a microscope. Now, in order for the pathologist to see clearly the tissue, we first need to stain it with a special chemical color called hematoxylin and eosin, or in short, H&E. This is staining colors the different morphological structures of the tissue with different colors of pink and purple. This is how it looks like. So this is a routine process that is done today for every biopsy. It's very cheap and it's very fast process. And the pathologist can look at the staining under the microscope and say important things about the tissue, for example, whether he thinks it's cancerous or not, what type of the cancer, and what is the grade of the cancer. But the information that the pathologist can extract from these images is somewhat limited. For example, the pathologist cannot infer from this staining what kind of gene mutations exist in the cancer, or what kind of molecular receptors for different hormones exist on the cancerous cells. In the case of breast cancer, for example, there are 3 hormones for which we need to check if there exist receptors to, for every case: estrogen, progesterone, and HER2. And the knowledge of whether there exist receptors or not eventually guides the treatment and give also estimation for the prognosis of the disease. If, for example, we know that we have estrogen receptors, or in short, ER, in the tumor, we know that the cancer probably consumes estrogen in order to survive. So we give medicine that blocks these receptors, and we prevent the tumor from getting estrogen. And this is how we can prevent the growth and even cure the disease. This is what's called hormonal therapy. So in order to know which kind of receptors we have, we need to do a different kind of chemical staining called immunohistochemistry. This is a brown color binded to the estrogen receptors, for example. And the pathologist looks at this staining under the microscope, and he needs to evaluate what is the percentage of brown epithelial cells here. If the percentage is positive, we will define this patient as ER positive status. And if the percentage is negative, meaning there aren't any receptors for estrogen, he will define this patient as ER negative status. So ER positive, we have receptors for estrogen. ER negative, we don't have receptors. And this is what guides the treatment for estrogen. So unlike hematoxylin and eosin, which is simple and fast and cheap, immunohistochemistry is a much more complicated process. For example, it costs much more. It takes time in which the patient needs to wait until he gets the treatment. It has some errors both in the staining process and the interpretation of the pathologist. It requires time of pathologist, which is one of the biggest bottlenecks today in diagnostics of cancer. And also, it requires technology that not even available in every country today. So our research question was whether we can use our computational methods, geometrical image processing, artificial intelligence, in order to improve this process. We started with a hypothesis that maybe the morphological structures that we see in this H&E image, maybe they contain information regarding the molecular status. So information that the pathologist cannot see with his own trained eyes. And maybe if there is this information, there exists some artificial intelligence algorithm that can predict directly from the H&E image the molecular expression of different receptors. So if we would be able to do that, we would get a zero cost practically and zero time solution, which is also much more consistent than what we have today. So we went to some pathologists and to ask about this idea, and they didn't really like it. They didn't believe. They said there is no way that you can infer what is the ER status of patient just by looking at the H&E slide. It's like looking at a closed door of a room and telling me what's inside the room. Indeed, there aren't any known features in the H&E image that indicate whether it's ER positive or ER negative that are known. And unlike typical AI algorithms that attempt to imitate or even improve some task that is already been done, in this case there is a task that has not been tried yet by a human. So let's move on to our system and the results that we got. Over the first year, we collected a data set of around 500 breast cancer patients with overall around 1,000 H&E images of tissue microarrays. Also, we had annotations for the ER status, positive or negative, for each one of the patients, and consequently also images. We came out eventually with this machine learning model where we start with H&E image. We segment it to some superpixel patches. We extract features with some arithmetic operations. We combine different H&E images of the same patient. And we eventually get features per patient. Then we train some model of, we used L1 regularized logistic regression in order to predict the outcome status, receptor status, from this feature vector. And we tried this on our data set with estrogen receptor. As a result, we obtained an accuracy of 68% in prediction of ER status. And this also can be measured by p-value, which measures the probability of this to happen by chance. And since the p-value is very low, it means that the probability it happened by chance is low. So probably there is correlation between the H&E image and the ER status. But we wanted to verify this and validate it on different data sets as well as different biomarkers. So in the second year of the project, we focused on collecting and arranging a data set. It took us a long time. We used scripts to automatically download from different public sources. It was a very challenging task. And we managed to collect over 20,000 H&E images of more than 5,000 breast cancer patients, and also annotations for 21 different biomarkers. So estrogen receptor, progesterone receptor, HER2, and another 18 of such. Also, we used a deep residual network because we had more data. I will not get into the model that we used, but we needed to use a model that will exploit the data and its variability. As a result, the p-value of each one of the tested biomarkers was significant, was low, meaning that probably there is correlation between the H&E image, the morphological structures, and each one of the biomarkers that we tested. Also, the accuracy for estrogen receptor was increased by around 15%. So now it's 82% accuracy for a prediction of estrogen receptor status directly from H&E images. So at this point, we used the best model that we could and all the data, and we obtained accuracy of 82%, and we asked ourselves whether we can still improve this somehow. So if we look at the softmax in the last layer, it doesn't output a binary prediction of ER negative or ER positive. It outputs a number between 0 and 1. This number indicates the probability of the result to be, for example, ER positive. And we call this number here the R-score. So the R-score is the probability for ER positive. For example, if the output of the machine learning during inference is close to 1, R-score close to 1, we would say this is probably ER positive. And if the R-score is close to 0, we would say this is probably ER-negative patient. But if the R-score is somewhere in the middle, maybe we can say we are not sure in the result, in the prediction. So we can define some measure of confidence here. We define this measure as a distance between R and the number 0.5. Now, the number 0.5 is actually not guaranteed to be in the most inconclusive result, but it can be manipulated to be by balancing the data in some way and the model. So once we have this confident measure of the predictions, we can consider only the confident outcomes. We can take only half of the patients, for example, for which we are most confident in our prediction and check our accuracy only there. Or we can take only 30% of the patients for whom we are most confident in, or only the 20% patients. And then we have this plot of accuracy vs the percent of patients we are most confident in. And we see that this plot is actually monotonically increasing. And we see that we reach beyond 90% accuracy and even beyond 95% accuracy of prediction of ER status directly from H&E stains. Also, what's interesting here is that there is a small subset of patients that we manage to predict over 97, 98 accuracy. This means that probably there are some morphological features that indicate whether it's ER positive or ER negative with a very high probability. So if we take the middle of this graph, meaning that we screen half of the patients, we already bypass the current immunohistochemical techniques that we have today, if we measure that by positive predictive value, negative predictive value, and other measures. So we used a data-driven approach, which means that we do not need to invent some new biological method in order to improve our results. We just need to train it on a lot of data. And to improve it, we just need more and more data. But at this point, we asked ourselves, how do we know that actually more data would improve the result? How do we know that we didn't reach saturation? How do we know that without having more data? So the idea was, instead of collecting more data, which was a very difficult task, let's reduce the amount of data and let's see what happened. So in this plot, we have in the y-axis, we have the AUC, area under row curve, and in the x-axis, we have the number of H&E images per patient. And in the data set, we had 14 H&E images per patient, and this was the AUC result. So if we reduce the data, we use only 12 H&E images per patient. This was the result. And if we use only 10, this would be the result. And we can go all the way to 1. And then we get this plot, and we see that it's actually monotonically increasing, but also we see it did not reach saturation because the slope here in the end is not 0. So probably, if we add more H&E images per patient, we would keep improving the results. Now, this was only cohort number 1, where we had a few hundreds of patients. In cohort number 2, we had a few thousands of patients, but only 3 H&E images. So probably if we had 14 H&E images per patient in cohort number 2, we would significantly increase the performance of the system. There is a great potential here. And we tried this not only on the estrogen receptor status, but also on progesterone, which is PR, HER2, and another biomarker relevant for breast cancer, Ki67. And not only on H&Es per patient, but also the number of patients in the cohort. Also, what would happen if we increase the resolution of the images? And what would happen if we increase the cut size of the image, using whole slide images, for example? And we saw that in every one of these parameters, the graphs didn't reach saturation. So we have a great potential here. Let's move on for the last few minutes for some interpretations. So we have an H&E image and some machine learning algorithm that predicts the molecular status from the H&E image. This means that the cancer it imprints some signature on the morphological structures, morphological signature, that we can see it in the H&E image. This signature contains information. The AI can detect this signature and extract the information regarding the molecular expression from it. Also, we can quantify this signature by the R-score that we said before. This is number between 0 and 1, which quantifies the strength of the signature. So if we take all the images, all the patients, and we sort them by the strength of the signature or by the R-score, we would get this plot. We see it's kind of uniformly distributed. Some have low R-scores, some have high R-scores, and some in the middle. And we can further split this graph now into patients that had ER status negative and patients that had ER status which is positive. And this is kind of expected because we expect that ER positives have higher R-score because R-score is the probability for ER positive. Also, we can split the ER negative patients by their progesterone status, PR. So ER negative patients, we have ER minus, PR minus, or ER minus, PR plus. Now we checked each one of these groups, the curve, the R-score curve of each one of these groups, and this is what we got. So the morphological signature measured by this R-score distribution of ER positive patients was similar to the morphological signature of ER minus, PR plus patients. This was very interesting because there are recent claims that the group of ER minus, PR plus do not actually exist. There are false positives, there are errors of the staining process or the interpretations of the pathologist. And actually today, ER minus, PR plus patients get the same treatment as ER plus. It works for them and we don't really understand why. The last thing I want to show you, we talked a little about the morphological signature. It's very hard to get intuition about features of a convolutional neural network, but maybe we can understand where the features are located in the image, where the information is extracted from. There are a lot of ways to manipulate the network in order to obtain this, and we used one of the ways, and this is what we got. So this is how the morphological signature looks like. The green parts are the parts of the CNN extracted most of the information from. And it was very interesting to see that most of the information is taken from epithelial regions, which contains the cancer and also the receptors for estrogen. But it was even more interesting to see that some information was taken from the stromal region. In the stromal region, we don't have the cancer. We don't have any receptors for estrogen, and yet we can predict from the stromal region the ER status. And we did an experiment. We cut out the stromal regions of hundreds of images, and we tested our system on them, and we actually managed to show that we can predict ER status based on a place where the cancer does not exist. This means that our body reacts to the cancer in such a way that we can predict from the reaction what is the molecular profile of the cancer. And doctors really like this idea. So just to conclude, we saw that the cancer imprints a morphological signature that contains information regarding molecular profile of the cancer, and that AI can detect this signature and extract this information and even predict the molecular profile better than current methods that we have today. We saw that more data has the potential to further improve our results. And finally, we saw that this technology can actually lead to new insights in the cancer research. Thank you very much.